Welcome back. In topic 2, we discussed the heat equation for conduction, convection, and radiation. In topic 3, we will learn how to use the first law of thermodynamics to connect those equations. A. System. A system is a group of materials of our interest. It is the studied target when we apply the first law of thermodynamics. The system can be defined as a control volume CV, which is a finite volume in space. For example, the red dashed line, which is the system boundary line, contains the system, which is the plane wall, and separates the system from the surroundings. The system can also be defined as a control surface, CS, which is a boundary surface of the control volume. For example, the blue dashed line contains the boundary surface. The difference between a control surface and a control volume is that the control surface contains no mass nor energy. Keep this in mind. B. First law equation for a system with energy generation. First, our system is a control volume CV. It is circled by the dashed line. The system is steady, indicating nothing will change over time. Therefore, change in any variable, such as energy, would be 0. On the boundary, the energy in the form of heat, work, and mass flow carrying enthalpy can enter the system and leave the system. If it into the system, we take the positive sign. If it is out of the system, we take the negative sign. Second, the variable Eg dot in the unit of watt represents the rate of energy generated within the system. For example, a house with a heater inside. If the heater is turned on, the heat produced from the heater will raise the temperature of the air. Therefore, the heater is a heat source. The heat produced from the heater per unit time is the variable Eg dot energy generation. In engineering applications, there are different heat sources. For example, electrical heater, nuclear radiator, chemical reactor. What is in common is that they will generate heat within the system. Now, if we put all energy together, the first law states that all the energy into the system minus all the energy out of the system plus the energy generation equal 0 for a steady system. Finally, if only heat enters the system and leaves the system, the first law is simplified to this: all the heat into the system minus all the heat out of the system plus energy generation equals 0 for our steady system. C. First law equation for a steady system without energy generation. It indicates variable Eg dot is 0 within the system. First, our system is control volume CV. It is circled by the dashed line. Only heat crossed boundary enters the system and leaves the system. Therefore, the first law states that all the energy, all the heat into the system minus all the heat out of the system equals 0 for a steady system without energy generation. Second, our system is a control surface, CS. The red dot dashed line contains the control surface. Only the heat enters and leaves the control surface. Therefore, the first law states that all the heat into the control surface equal all the heat leaving the control surface. Third, the first law can also applied to the heat flux and heat rate per unit length. At this point, we covered topic 3. If we do quick summary, here is the key point. We defined first law for control volume and control surface. The objective of topic 3 is for you to be able to apply the first law to solve heat transfer problems. Next, let's practice the example 1-3. Again, pause the video, do the problem on your own, then compare your solution with the instructors. As you can see, we have a spherical probe with a diameter 0.5 meter. It contains electrons which dissipate heat at this rate. Therefore, electrons is a heat source. The probe surface at a temperature Ts with emissivity 0.8. The probe travels in the deep space, which is assumed as a large surrounding at temperature 0 Kelvin. We're interested in finding the temperature of probe surface. Where do we start? Let's do the analysis. In deep space, there's no air, there's no water. Therefore, only radiation heat transfer mode can exist. Next, there's temperature difference between probe surface and a deep space surface. Therefore, there's a radiation heat flow leaving the probe. Next, we can define our control volume circled by the dashed line. Then apply the first law equation to our system defined. Since there's no heat entering the system, so we have a 0 here. We have a leaving radiation heat, so we minus Q radiation. Since we have heat source within the probe, therefore we plus variable Eg dot equals 0 for a steady system. Next, we need select the heat equation for radiation heat rate. Equation 2 represents the radiation heat rate. In this equation, A is the probe surface area. Since we know the diameter, we can calculate the area AS, which is 4 pi r squared. We know epsilon, which is 0.8. Sigma is a constant. We have an unknown here. We know the T surrounding temperature. So this is good because it contains our unknown. However, we don't have any equation for energy generation. How do we get this value? Let's go back to our system. You may have noticed that heat rate per unit of volume is given within the system. Therefore, we can calculate the energy generation value by using the heat rate per unit volume times the probe volume to get the value, which is 150 watt. Next, we can plug into the equation 2 and value 150 watt of energy generation into equation 1 to get equation 4. Finally, we'll plug into numbers into equation 4 to generate 0 minus 4 pi r squared, which is area, time emissivity 0.8 time Boltzmann constant with this unit time the temperature Ts to the 4th power minus 0, then plus 150 watt equals 0. Solve for Ts to get the temperature of probe surface value. In summary, the step we followed is that you first understand the problem, then identify all the heat transfer mode. Next, define your system and apply the first law. Then you select the proper equation for the items in the first law equation. Finally, you plug into the numbers to get unknown. See you next time.